We are a team of students from VIT Chennai in the Electronics and Computer Engineering department. Our team members include Sahitya Gupta, Sahil Kumar, Vijay and Pratik. Today, we are excited to present our topic on parameter estimation of PV system models using ANNML-based method. This research is aimed at optimizing the performance of PV modules by precisely determining and tuning the important parameters that affect their performance and lifespan. We will be discussing the various methods used for parameter estimation and how our team has developed an efficient ANN model to achieve accurate and stable results. PV systems are a great way to generate electricity from the sun, but understanding how they work can be complicated. That's where the PVLib library comes in. With PVLib, you can quickly and accurately simulate the behavior of PV modules under different environmental conditions. The single diode model is a widely used model for simulating a PV cell's electrical behavior. PVLib's implementation of the single diode model includes several parameters that impact the accuracy of the model, such as temperature and irradiance. To calculate the peak power for an instant, you need to know the solar position, irradiance, temperature, and wind speed. Adjusting these values can have a significant impact on the output of your PV system, so it's important to understand their intrinsic properties and their role in the system. Parameter estimation and tuning are crucial for optimizing the performance of PV modules. It involves determining and tuning the important parameters that affect the performance of the solar module and diagnosing faults or defects in PV cells that can affect their performance and lifespan. While several methods like curve fitting, incremental conductance method, fuzzy logic, genetic algorithms, and particle swarm optimization have been applied for these tasks, they may not always be as accurate as machine learning (ML) methods. One such ML method is artificial neural networks (ANNs). ANNs utilize neurons to process information and generate outputs. These networks are trained using a dataset of known input-output pairs to develop a mathematical model of the system. ANNs can learn from data without prior knowledge or assumptions about the PV cell, making them adaptable to different types of PV cells and environmental conditions, leading to more accurate parameter estimation. The architecture of the ANN, such as the total number of input and hidden layers, neuron selection, and the activation function used, along with the learning rate, batch size, and number of epochs, are important hyperparameters to define the ANN architecture. For this project, the activation function used was ReLU, while ADAM was the optimizer and mean squared error (MSE) was considered for monitoring the loss during training. The model was trained for 30 epochs and the loss was reduced to less than 0.0001, indicating successful implementation of the model. To evaluate the efficiency of the built model for its stability and accuracy, a Bland-Altman test was conducted. This statistical analysis test compares the predicted and measured values and checks the difference. If it is within mu plus or minus 2 sigma 95% limits of acceptability, the model is said to be efficient. In this case, most of the data points lie inside the limit of agreement, confirming the accuracy of the model. This ANN-based method for parameter estimation of PV system models was applied, considering the irradiance and temperature as its input pair and power as output. The coefficient of determination output was measured to be higher than 99% in constant state, indicating an efficient ANN model. The ANN approach has produced better values for parameter estimation than metaheuristic algorithms and soft computing algorithms. The output shows higher precision in mapping the parameter values, which in response decreased the mean squared error significantly. Let's now move on to the demo of the code. In this demo, we will be showing you how our machine learning model accurately estimates the performance parameters of a solar panel based on its temperature and irradiance levels. We will input some sample values for temperature and irradiance and show you how the model predicts the corresponding power output of the solar panel. So, let's get started with the demo. This code is written in Python and uses the Pandas library for data analysis, the NumPy library for mathematical operations, and the TensorFlow library for machine learning. The code reads data from a CSV file and selects 3 specific columns using the useCalls parameter. It then checks for any missing values in the data frame using the isNull function. Next, the code calculates the Pearson correlation coefficient between the 3 selected columns using the NP_do_coef function and stores it in the Pearson variable. It then normalizes the data in the columns by dividing them by different values. The code then creates a heat map plot of the Pearson correlation coefficients using the SNS.heatmap function from the Seaborn library. After that, the code separates the target variable PM original from the rest of the data frame and splits the data into training and testing sets using the train test split function from the scikit-learn library. It then creates a neural network model using the Keras library with 4 layers, the first 3 with 5 neurons and the last with 1 neuron, and uses the Adam optimizer and the mus loss function. The code then trains the model on the training data, storing the training history in the model history list. It also plots the training and validation loss over the number of epochs. Finally, the code extracts and prints the weights and biases of each layer of the trained model using the getWeights function. Overall, this code reads data, checks for missing values, calculates correlations, normalizes the data, creates a visualization, builds a neural network model, trains the model, and extracts the learned weights and biases. After adjusting the parameters in the model and running the code provided by Nuldeo, we were able to improve the performance of our model. Before training, the mean squared error MSE was 638.93, the root mean squared error RMSE was 25.28, and the R2 score of the model was 0.87. The standard deviation was 16.33 and the mean error M8 was 19.29. After training, we were able to significantly improve the model's performance. The MSA decreased to 4.43 and the RMSE decreased to 2.10. The R2 score of the model increased to 0.99, indicating that the model is a good fit for the data. The standard deviation decreased to 1.95 and the mean error M8 decreased to -0.78. Overall, the trained model is much better at predicting the values of PM original, and we can use it to make more accurate predictions in the future.
Thank you.